When I got a device like this is a Sanyo 2050. It is a 50-watt vintage amplifier. I believe it is built on early 80s. When we start working on this kind of a device, most of the time we are focused on how big the transformer they have, will that be able to provide enough power to that unit to drive the power they declare, and what is the power unit they have. Are they using the good component? Are the transistors good quality, or the IC they're using is reliable? So all this kind of a thing will catch our eyes. But even though I recall when I'm in the college, we do pay a lot of attention in transistor, how they're linear, and what is the parameter of that. And we pay very little attention on the capacitor, sure, resistor either. Right? So when we work in this kind of the vintage equipment, there's one procedure is we need to do the recap. A lot of people agree we need to recap the equipment because the capacitor usually get aged, and some even get worse, like they leaking or they just lost capacitance. But yeah, sure, you can close your eye to replace the whole thing, to do everything brand new. But some of the curiosity always drive me say, are those capacitors we replace are really bad? And at least I want to know what is the status they are. Are they actually lost half of the capacitance, or they still good? Yeah, in this video, what I'm trying to do is do some experiment. Also, I did a lot of reading and research in internet to get the information put together, to get some understanding, some knowledge for myself about the capacitor. I will use this small RC circuit to charge the capacitor. This is a small device. 44-volt DC are from the amplifier main power. This current flows through this R and charge the capacitor. And I have a voltmeter connect to the capacitor to monitor the voltage of the charge. Once I turn on this switch, the voltage, the current from the amplifier will charge the capacitor. Let's focus on the voltage rating of the capacitor to see what it looks like. Let's start it. Now the charging speed is very fast. Right now it's in a linear speed. The voltage in an average speed going up. Now we can see it slow down. Let's go to the oscilloscope to see what happens when we see the capacitor is charging. This is the beginning of the charging. The capacitor is starting from the 0 volt, and this is the end of the charging. The capacitor is supposed to have the same voltage of the power supply. When it started to charge, the capacitor's voltage started rising. In this section, we can see the voltage rising. It's similar to a linear speed. The going up. By the time the voltage rise to a certain point, and the charging is slowed down. You see the curve is slowed down. At the end of the charging, it can be very slow. It takes a very long time to reach the full charge. I connected the signal generator to the device. The scope read the direct connect to the device with the capacitor is not connected. Let's see what signal we feed to the scope. We have peak-to-peak 9.91 volt, 1 Hz square wave. After the capacitor connect to the device, we can see the waveform change from the square wave to the charge wave. This is the capacitor charge diagram. Let's disconnect that to try it again. After we disconnect, we can see this is a 1 Hz square wave. From here, we can see the capacitor can be discharged. And by the time the voltage is rising in this side, and it will charge the capacitor. Because the capacitor have the delay of the voltage, so this upward gonna become a curve like this, a curve, until the capacitor in full charge, it will reach this area. Okay, let's reconnect it. See? The square waveform charge the capacitor. The capacitor voltage will rise from 0 all the way to the peak of the signal's voltage. Let's save this waveform and we can use it to calculate what is the capacitance of the capacitor. I'll name this as C003 and save it as CSV file. Save it. Okay, now the waveform is saved. Let's load the waveform. We can using the waveform to do the calculation. We don't need to deal with the dynamic form. when the signal is charging the capacitor. Okay, now this is static form. We save from the real charge. Let's do the math. Tau equal RC. Tau is the time when the capacitor charge. R is the resistance over here. C is the one we try to figure out. If we convert this express to C equal tau R, we just needed the tau. R we already know, so we can calculate the C. So how can get the tau? The tau is defined as 3.2% from the peak to peak voltage when the capacitance charge to 3.2% of the peak to peak voltage, and the time span is the tau. So this is the tau. If we can find this point, we get this tau put in here, we will be able to using the R together to calculate capacitance of the capacitor. Let's use the tool from the scope to get the tau. We start from the 0 point and get up to 6.1 volt. Now I get 6.09 volt. It's about there. And the time reading is 99.7 milliseconds. Okay, now we get the tau is 9.97 milliseconds. At this point, is the capacitor is charged to 63.2% of the source voltage. The data, we got the data. When the voltage is 6.1 volt in the capacitor, the tau is 99.7 milliseconds. It is a millisecond, so we needed to divide by 1,000 to get a second. Now we just put this thing into the expression to see C equal 99.7 divided by the R, and we times 3 because this is a millisecond, so we only times 10 to 3 power. So we call the capacitance is 21.44 microfarad. I don't know what is in the label. I didn't read it yet. Then we can double check with the label, and we also verify that with another handheld device to see if that calculation make any sense to us. Actually, this is a new capacitor I got from Mauser not too long ago. It is a 22 microfarad, 16 volt. Let's double check with the handheld device. Let's put the capacitor in the DE500 to test it. I put it in 120 Hertz, and I got the reading is 20 microfarad. Based on the label of the capacitor and the DE5000 testing, we get the result. It's pretty close because the capacitance tolerance is about 20%. So I would say 21, 20, it is not a big deal. Before we got all this calculation, we don't even know what is the range or whatever the capacitor will have. Then we do purely in the live experiment, and then we get this result. It's pretty close to the real capacitor data. I think we can think this experiment is success. This is a capacitor I took out from a vintage amplifier. I bet it is over at least 35 years old, at least. So I don't know what is the exactly capacitance it can have. Let's put it in the real test to see. This is the waveform we get from the capacitor charging. It's a bit of a different than the one we see before. You see? Let's take out the capacitor to see the waveform. So this is the charge form. It's still 1 Hz square form. But when you charge the capacitor, we see that from the 0 point, the capacitor, the voltage rising, but it did not get to the peak. Because what? This capacitor is a little bit bigger than the one we're using before. The 1 Hz waveform does not have enough current to charge this capacitor all the way to the peak. So the capacitor is big. So the capacitor has not get to the full charge. The waveform already dropped. So see that the capacitor is start to discharge from here. So this waveform is not correct. We cannot use this waveform to do the calculation. So what can we do? Because we don't know the capacitor, what is capacitance it is. Now we have to change our RC parameter to make the waveform look like the one we have using before. I reduced the R value from 4.7K to 1K. Now the R value is smaller, so with the same voltage of the signal, the charge current will be bigger than the last resistor. Now let's go back to see what is the waveform look like. And now we get the full charge waveform. Let's double check if this capacitor actually charged to the peak-to-peak voltage. We know this is 0 point, and this is the maximum value, maximum voltage of the signal. Let's double check that. I will disconnect the capacitor. You see the waveform? The 1 Hz square form, when we connect it, yeah, we can see the capacitor actually charged to all the way to the peak of the waveform. Now let's see what is the peak-to-peak value of the waveform right now. It's 10.1 volt. Let's make a copy of this waveform. We can save the data. We're using C004 as the name. Save as CSV file. Save it. After we save this waveform, we can reload that. Then we don't need to deal with that dynamic form. Now we get the C004. Okay, now this is a static form. By now, we need to go back to the map again. Now the value of the R is changed. Once we change the R value, it slightly changes the VS value also, because this generator is not very powerful, not very robotic. So once the R changes, it draws more current from the generator. It drops the voltage is slightly changed. Now we get the new voltage of the signal is 10 volt. So sure, 63.2% is gonna be 6.32 volt. The R value changes to 1000 ohm, it's 1K. And we're gonna check the tau. The tau will be the VC reached 6.32 volt. When I measured from 0 to 6.32 volt, the charge current, the charge voltage, we got tau is 94.4 milliseconds. We can use this data to do the recalculation of the capacitance. After I put the 94.4 milliseconds into the same expression, because this is 1K. Now we can directly get 94.4 microfarad is the capacitance of the capacitor we're testing. Let's go back to the label. And the label, it is 25 volt 100 microfarad capacitor. I put it in the DE 5000 to double check. With the 120 Hz frequency testing, we got 75.22 microfarad capacitance of this capacitor. Compared to the data we get, it is slightly different. But again, capacitor always have some tolerance. And also we need to remember this capacitor is a capacitor. I doing the recap, I got it from one of the old amplifier. So it's been out there for many decades. So I believe this capacitor, this testing result is pretty close. Yeah, it's pretty close to the real value. Let's do something more aggressive. I have a 63 volt 4700 microfarad capacitor from the other amplifier. we know this is the main power filter capacitor. Do we be able to using this method to test it? Let's try that. We still get the 1 Hz square waveform. We're using that to test two of our capacitor. The value is pretty close. Let's try this big one. Let's connect it. As you can see, the waveform totally got eat up because the capacitor it's too big. So when the small signal generator feed the signal to the capacitance too big, so the voltage only slightly rise. It not even be able to hit like I believe it's not 1 or 2 volt. So for this kind of a case, I don't believe we can use this generator and this combination of the R and C to test this capacitor. Yeah. If we try to using the same method to test this big capacitor, first thing we need to do is what? We need to have a signal generator can provide much bigger current to be able to charge this capacitor to the certain voltage. This first thing. And second thing is what? When this 0 point voltage riding, the capacitor is slowly charging. And they need a lot long time, maybe minute, to be able to charge that capacitor all the way to the peak. So we probably need this waveform way larger than this. Okay? We need to have a very long period of time waiting for this capacitor charging. So the minimum frequency of my generator is just like 1 Hz. Yeah, you won't be able to handle this kind of a big job. So how do we just get some confidence of this old capacitor? And yeah, sure, we can go by the multimeter or just go by the handheld equipment, but that small device only have like a 9 volt battery inside, so the testing environment will be much lower voltage. It's not a real environment for the capacitor which will work on. I have the other video to do some kind of roughly checking of the capacitance for those old big capacitor. It's based on the same theories of this. Based on the same theories, because we need to charge very long time. It doesn't matter how long. If I get the voltage of the 3.2, then I can use a multimeter and a stopwatch to watch my voltage riding and to get the time. The time is tau, and use that time to calculate capacitance. Yeah, I have another video to do that. I think I get pretty close to that.